Okay, so those were some conditions and some stories on, the lead and tin system, and alike with the silver, copper system for sterling coins, for example. And now let's look at an analogous situation for something called a eutectoid. So eutectoid is related but has a very unique definition. So a eutectoid here is a reaction where one solid phase is going to transform into two other unique solid phases. So to be very clear there, the initial solid, let's make sure it's called differently, so we're going to call that solid 2, is going to be in equilibrium with two different solids, solid 1 and solid 3. So we will not see the alpha, beta, or what have you matching across either of these solids. All three are going to be unique. Okay, so the eutectoid, again, is defined as the point where one solid transforms into two other unique solid phases. We'll see it in the iron-carbon system, where at a particular temperature point, gamma iron with carbon will be in equilibrium with alpha iron and iron carbide, an intermetallic ceramic-like material called cementite. Okay, and the point of this, where this equilibrium is, the point where this eutectoid is at a temperature of 727 Celsius, and low content of carbon here, only 0.76 weight percent carbon. Okay, so let's look at that. And here's the phase diagram for that iron-carbon system. So the iron-carbon phase diagram, all the unique kind of phases are mostly located at low carbon content. So notice the x-axis range. We're in carbon content, we are between 0 and about 6.7 carbon weight percent. Above 6.8%, the dominant structure is just iron carbide, this cementite material. So you can see that kind of being the limit here is we can consider modest temperature materials, and if we were to consider higher carbon content, we'd be largely Fe3C cementite. Okay. So, a couple of important points. We've seen Eutectics and Eutectoids. So perhaps try your memory and see if you can find the eutectic point where a liquid would transition into two solids. Yes, so hopefully you're looking right at this point. Two solids, a melt point here that's lower than the other two extremes. And a eutectoid point this time, we have to go from a solid. So here we have a gamma FCC material. So it's a face-centered cubic iron. And we have to transition into two other solids. And so here, one solid is the Fe3C, iron carbide, cementite, and the other one is the alpha, a body-centered cubic iron this time. So in transitioning right at that point, from higher temperature to lower temperature, one solid will become two different solids as we walk across this 727 eutectoid point. At that modest carbon concentration. Okay, so that is to say, we know that at around this 0.76 weight percent carbon and at a temperature around 900 degrees C, we would expect FCC iron with carbon in interstitial sites, and the material would be packed, and we would have grains and grain boundaries separating the grains from one another. And as we were to cool down spontaneously right across the 727 temperature mark, all the gamma is going to transition into two different solid phases, some forming alpha, some forming this cementite. Okay, and so this is our new diagram for that. Notice that roughly, as the diagram is tried to indicate, grains that we once had have largely given us the outline where these two materials are. So one gamma grain has now split into two different phases and an alpha with these striped regions of the cementite between. And you see that to the next grain, etc. So we've inherited this microstructure from the gamma grains that we had at warmer temperature. Okay, and then when you actually go and do the microscopy, you can see here the exact same features that we've outlined here. Former grain boundaries and these layers of alternating alpha and iron carbide cementite. Okay, so what we have here is a perfect kind of composite material where we have very hard ceramic type material called cementite, and this is layered in between the soft ferrite that is alpha iron, that is body center cubic iron. And so this balance between the hard and soft is what gives this material its strength. Okay. Good. So let's end with just a problem. Let's see if we can determine how much of this cementite would form at 726 degrees C in 100 grams of this stainless steel that is about 0.4% carbon. So use various tie lines that you know how to use to help answer this question. And let's see if you can answer the question. So try to determine in grams how much of this stuff will form out of 100 grams of this iron carbon system at the temperature condition described. Okay, so if you've paused the video and had a chance to try this, we'll start. So our approach is to be able to use a tie line to help us with the weight fraction of the iron carbide. So we're interested in weight fraction of FeC, Fe3C. So we also know that we were at about 0.4% carbon, so that's just over here about. Okay, so we're not at the Eutectoid, but we're to the left of it. And we're just below this temperature here. Okay, so we're right about here. And so if we apply our tie line, we're going to isothermally be there and all the way to here. And if we're interested in the iron carbide, we're going to use the smaller segment of this tie line. So if this is 0.4, and this question has kind of already helped us here, the x-coordinate for the point where this tie line meets the boundary here with the alpha carbon at it, that is the sliver territory here, we're at an x-coordinate there of just 0.0228%. Very, very low for this little point down here as we drop down. Okay, so we're going to be a numerator after all that. We're going to be 0.4 minus 0.022%. And now we have to do a denominator that is the whole thing. So we already knew our upper limit here was 6.7, given that this is a boundary. Okay, so we're going to be 6.7 minus the tiny amount there, the 0.022. So that would give us our fraction. So this is going to be a weight fraction of about 0.057 in the weight fraction for the iron carbide. And of course, if we know that there's 100 grams, so the total mass here of the sample is, of course, the 100 grams. So that means mass, that is the iron carbide. Sorry. Is going to be equal to this fraction times the 100 grams. So that's going to be 5.7 grams. Of this iron carbide is going to form. Okay, so while we might be kind of up at this upper condition for mixing, once we kind of drop the temperature low enough and we exceed the and bring the temperature to about 726 degrees, throughout that structure is going to be 5.7 grams of this iron carbide in that layered format that we saw earlier. Okay, so with that, I think we're done, and hopefully you were able to follow that. So I'll just clean up my notes so you can see the polished version here if you want. And we'll continue with examples in our homework and quizzes as needed. Okay, very good. See you next time.